7 zeros. All right.
Or you can say.
This is jumping like from here to here or something?
These are separate. This side right here and this side, this would be like the loudness scale. This would be our acoustic power side.
Okay, because you went from this and then you mentioned 70.
I'm really, it wasn't supposed to be this in depth. I'm trying to keep it light. I'm really trying to keep it light because all of the explanation.
You don't know.
No, it's not that I don't know. I don't want to get into the depths of it because you don't have to know that for your exam. Right? So I don't want to teach, and again, the exam doesn't have math on it. So I don't want to teach you a whole big formula for a math problem when you're not going to be doing this on the exam. So that's why I'm trying to keep it light because you won't be sitting out working out, oh, what's the logarithmic scale for 30 decibels, 27? You won't be doing that. You won't be doing that. All right? So we're moving on. We're moving on because I have to get you. We're moving on. Get with me after class. All right? So done with logarithms and decibels. Okay? Again, I gave you guys that chart. Take heed to that chart. Try to remember that chart. It's something I'm asking you guys to do. All right? So let's talk about attenuation, guys. Attenuation, guys, I made this PowerPoint different. Tried to make it like flashcards. So every time we have like a important term, I just made it like a slide by itself. And you have the definition and maybe an illustration if it has an illustration. Okay? So we're talking about attenuation now. Attenuation is the decrease in intensity, amplitude, and power as sound travels. And we know that. Or weakening as sound propagates. Okay? That's my image right there. As sound travels, the amplitude, intensity, the bigness of this pulse right here is getting weaker as it travels. Okay? That's what attenuation is. All right? Attenuation is determined by two factors, guys. Attenuation is determined by two factors. Number one would be the path length, meaning that the longer sound travels, the weaker it's going to get. Okay? No matter what the intensity is, the longer sound travels, the weaker it's going to get. Okay? And the other factor would be the frequency of sound. Okay? The higher the frequency of sound, the more attenuation. Okay? Think about it.
Yeah.
Think about it in general sense. That's why we can't use a 12 megahertz transducer to do an abdomen, because the sound is going to be attenuated to the point where it won't penetrate to a certain level of depth. Okay? So we use a 12 megahertz transducer on an abdomen, we probably can only see about, 7-8 centimeters deep into the body. And that's why we use a lower frequency transducer like the 5, because those longer sound waves, they're going to be able to penetrate the body deeper.
Did you say the higher the frequency, the more attenuation?
Absolutely. Absolutely. Okay, so our two factors that determine attenuation are going to be our path length and our frequency. All right? Real easy to remember these guys because both path length and attenuation are directly related to attenuation. Path length and frequency are directly related to attenuation. So, the longer the path length, the higher the attenuation. Okay? The higher the frequency, the higher the amount of attenuation. Just think of it in a general sense when you're doing an exam. That's why I can't see deep with a 12 megahertz transducer, but I can see deep with a 5 megahertz transducer. Okay? So again, the pad length, the further the sound travels, the greater the attenuation and the weaker the beam gets. All right? With frequency of sound, attenuation is greater in higher frequency sound than in lower frequency sound. The higher the frequency, the more attenuation. Okay? So the path length, the two factors that affect attenuation, path length and frequency, are directly related to attenuation. All right? Like our speed, propagation speed, and stiffness. Okay. again, this will be our intensity, our amplitude, our strength of our wave. Over time, you see that intensity is getting less and less and less as it travels over time. All right. Attenuation is measured in decibels as well, and is reported as a relative change, not an absolute change, guys. Remember that term relative means. So if a wave propagates and the intensity is reduced 1/10 to its original value, we can say that wave has attenuated 10 decibels. Even though I know that that's a negative 10 decibels, right?
Mm-hmm.
But because I use the term attenuated, we assume that's a loss of energy or weakening of the beam intensity. So we don't have to use negative 10. I can just say that beam attenuated 10 decibels. Okay? So when reporting attenuation in decibels, the negative sign is often omitted because we know attenuation to mean a weakening or decrease. Therefore, decibels must be negative when we're talking about attenuation.
But here you're saying you omit the sign. That means we're not going to put negative
Exactly.
10.
If I'm using the term attenuated, exactly.
Oh, okay.
Exactly. Exactly.
Isn't a fraction just a negative? A fraction isn't that negative? Because you're like.
I mean, you're taking
What
less
is
than
it?
one. You're taking less than one.
والواحد عنده برد يعني.
Okay. Any questions on our two determining factors of attenuation? What's attenuation when? Weakening of the sound beam over time. Okay.
يعني خليهم أربعة أحلى.
Ms. Cecile, what are our two determining factors of attenuation?
What affected
What are our two factors that determine attenuation?
the length
Okay.
and the time, no, frequency.
Frequency. They told you like 3 times. Okay.
It just dropped from my head. From my head.
So guys, now I got 15 minutes left. Hopefully I probably get through scatter. Alright. So there are also 3 processes that contribute to attenuation. Not that determine attenuation like path length and frequency. There are three processes that contribute to attenuation. Those are going to be reflection. So again, remember, either our sound when it travels and it propagates in the body, either that sound is going to be reflected back to the transducer, it's going to scatter, or it's going to be absorbed, such as bone. It will be absorbed in bone. Okay? So our 3 processes are going to be reflection, scattering, and absorption.
How do you contribute?
I'm going to talk about it right now. Okay. So the first one is going to be reflection. This occurs when the sound strikes a boundary and some of the wave's energy is redirected or reflected back to the source. Again, when that sound hits different interfaces, when it hits the liver, some of the sound is going to bounce back. As it travels through the liver and hits the posterior border of that liver, that sound is going to reflect and bounce back. As it goes deeper and hits that kidney, the anterior border of that kidney, some of that sound is going to reflect and keep traveling. Okay, so every interface that sound hits, some of that sound is going to reflect back to the transducer. Okay, again, as that sound keeps traveling, it's energy. Remember, it's just a transfer of energy. Energy is going to be lost as some sound is being reflected back, some sound is still being transmitted. Okay, again, that's why we have to.
The loss of energy depends on the organ that it's absorbing, how fast each organ might be absorbing that energy.
Or reflecting.
Or reflecting.
Or transmitting. Definitely. Okay. This reflection weakens this portion of the wave and it continues in the forward direction, such as in figure 6.3. You see in 6.3 that the green transmitted signal is strong, but that reflected signal come back is a lot weaker, right? But remember, we're concerned about the degree of attenuation just as much as we're concerned about the degree of amplification, right? So when we get that weak signal to come back, that's when we have to amplify that sound. Okay? How do we amplify our sound? What are ways I just told you about today? Our 2 ways. Doing reception. The 2 ways I talked about today, you do it every day.
Gain control.
Overall gain.
Power.
The TGC. Remember, acoustic power is doing transmission. That's before it gets to the patient. Okay? We're actually changing the intensity of the beam as it's being transmitted. Okay? When we change the intensity of the reflected beam, those are going to be our gain controllers, TGC, and our overall gain. Okay? That occurs during reception because reflected signals come back weaker than the transmitted signals. Okay? Reflection is likely to occur when the dimension of the boundary is large, okay, and more than a few wavelengths of the sound. What's our typical values for wavelength? Anybody remember?
For the body?
0.1 to 0.8 millimeters. 0.1 to 0.8 millimeters. So if we have a structure that is more than a few wavelengths of sound, 0.1 to 0.2 millimeters, then it's likely that sound of whatever organ or whatever we're looking at is going to be reflected back to the transducer. Okay. There are 2 types of reflection created in soft tissue. Those are specular and diffuse reflection. Okay. Specular and diffuse reflections. Okay. This depends on the nature of the interface, though, and the sound that it strikes. Okay. So let's talk about specular reflection. So specular reflection occurs when the boundary is smooth, such as the shape of the kidney. It's a smooth boundary, right? It's a smooth boundary. It's kind of rounded. It's a real smooth boundary. The sound is reflected only in one direction and in an organized manner. Okay? Whatever the angle that the sound is being transmitted is gonna reflect back in that same angle. Okay? So the angle of the initial angle is gonna equal the angle of reflection. Okay? So this occurs when light waves strike a mirror, for example. So when you think of specular reflection, I want you to think of a mirror. Okay? A limitation of specular reflection is that specular reflectors, once they're slightly off axis, the reflector does not return to the transducer. Think about that, right? If our beam is coming at an angle, you guys don't know this yet, but the beam doesn't automatically shoot straight down. The beam has steering capabilities. So the beam is sweeping like this actually, and we'll talk about that when we talk about the transducer. The beam isn't actually just coming down in a straight line to the body, to the anatomy. How the beam works is gonna send it out at this angle, it's gonna send it out at this angle, and it's gonna send it straight down. Okay? So whatever angle, the thing about that is the limitation that we don't get all our reflections back. Okay? But that's why it comes at many different angles, so we can get as much information as possible. Okay? So just think about it, guys. When you guys, especially my ladies, in your mirror, right? If I'm not looking directly in my mirror, I can see myself, right? But if I turn my angle, you guys can see me, right? Right? But now I look at myself, you can't see me. Correct? So the angle that I'm looking at is also going to equal the angle of reflection. Okay? So if I turn my angle to you guys, everybody can see me real nice in the mirror. Hey, Sophia, got the mean mug on. I see you right there. Look at my brow. But if I'm looking directly in front of the mirror, like this young lady right here, I'm going to get those reflections are going to come straight back to me. Okay? So that's what this means. That, yeah, I'm looking, even though my face isn't necessarily a smooth boundary, but the angle of the angle that I'm looking at is gonna equal the angle of reflection. That's the whole point of that. So when you think of specular reflection, think about a mirror. You're good over.